Okay, so instead of DSP, we use making actually a DSP problem solving course. Same material. For historic reasons, I have two different names and different implementation codes for those uh, one material. Okay. Um, Enrollment. So if you want to have a 3 or 5 credits from Metropolia, then you need to register. Otherwise, don't. And basically, let me go through some of that material now. Okay. Then, and there are also videos from my previous years. Perfect. I will add some of this material that I'm recording now also to the website. But anyways, so let's go and see what the course descriptions looks like. Yeah, signal fundamentals, system fundamentals, system responses. So this is basically exactly what you should be learning from this package. So it fits well. Each of these actually also have a slideshow. So, whoops. So what we are talking about here is a brief summary of digital signal processing. There have been plenty of big books written on this stuff. Okay, if you like books, I have a couple of good books for the engineers. This is excellent. Sanjit K. Mitra, Digital Signal Processing. It's already say old book, but still valid. It also have the MATLAB exercises. By the way, did you install the campus MATLAB license to your computers? Okay, if you didn't, you should do it. So since you have a campus license, you can actually download the full version of the MATLAB into your computer. Yeah, that's an excellent tool for digital signal processing. Okay, then there's a nice textbook on, or actually it's in an electronic book, Stephen W. Smith's Scientist and Engineer's Guide to the Digital Signal Processing, very practical oriented digital signal processing book. Oh, right. Motivation, practical and useful topic. I need this because Norbert told me so. That's your answer. All right. What you already should have is the fundamentals, like the mathematics fundamentals. The foundation of digital signal processing is in mathematics, in discrete mathematics. But the digital signal processing is very practical. It's almost like not math at all. Sure. Okay, it uses the say mathematical tools, but it's really practical kind of thing. And some special like series Fourier transform, Z transform to understand the spectrum and time. What is the difference? Not much. Topics, yeah, we will cover those. Okay. Frequently appearing mistakes. Okay, this is a worth of checking. I have a ongoing list for the exercise returns, and this list actually, if you read it and prevent those mistakes, you will get a score of good numbers from the exercises. So basically, one mistake is I'm actually asking you to send a link to your return form. Not the form itself, but linked to that one. One good way of missing points is that link does not open because sharing settings are not okay. Very simple mistake to do. I do it sometimes myself. Okay, so I already lost 1 point because of the previous website didn't open to you. All right. But anyways, that's the kind of frequently appearing mistakes you should be aware of. I started giving the same course on year 2000 in Frankfurt University Applied Sciences as a the week. 1 week intensive course, and actually this list is based on, some of them have been, frequently appearing mistakes since then. And the link sharing is actually one of the first ones. Okay, assessment. In Finnish we have 1 to 5 scale. In here you have 5 to 1 scale. Okay, so it's opposite. So in Finnish system 5 is the best. In German system that's fail, right? But anyways, 90% means excellent, and then it basically goes 10% steps until the very satisfactory, and then the still passing grade less than 40%. Oh well, no, 40% or more satisfactory. That's still passing grade. So it's 4 in your scale. Nobody wants them, but I don't have any hesitation of giving you 1 if you deserve it. Okay, exercises. Yes, exercises. Each exercise is 10 points, plus 2 exercises will appear here. So after I'm left, 1 exercise in embedded systems, meaning what should be taken into account if you have only fixed point precision calculations, only integer kind of calculations. Another is actually quite nice topic for engineers is the regression. All right, scoreboard. That seems to be the last year's scoreboard. Yeah, DSP problem solving 3. And let's see, those look like Daniel Rodriguez, Javier, Mario, Miguel Eduardo. It sounds like Spain, right? That was from Alcalá University Applied Sciences. Okay, so it's scoreboard, which is more or less in real time when you have returned an exercise. When I start open it, I also open my part of that the sheet and start giving you points. All right, and see, I haven't got any hesitation of giving those ones. It's a passing grade. All right. Any questions about the general? Okay, good. Signals. Let's start covering the signals part. Digital signals, what they are all about. This is supposed to be 30 centimeters higher, but anyways. So one good example of digital signal processing is voice recording. For example, on your mobile phone or any device, you basically have some sound source, for example, a cat, and then a spine dog thinking of bone, and listening and having a recorder in between, sampling recorder and in between. So, all right, what kind of part we need? This is the analog part, gain, filtering, low pass filtering, and then sample hold, and finally the A to D conversion. This is supposed to be okay for you, right? You have been doing your analog electronics. That's usually at the last topics covered in analog electronics is how to make it the digital. So if you're taking a look at the signal, what it looks like on each of these steps, first we have a weak signal with some noise. But anyways, if you oscilloscope with the oscilloscope, you can actually see it better. Okay, after gain, you should actually fit that one as well as possible to the A to D conversion range. And do the low pass filtering, which is anti-alias filter. You have to get rid of the spectral components which are higher than half of the sampling rate. That's the Shannon's theorem on sampling. And then sample hold. Signal is still analog, meaning the value can be anything, but timing actually it's already discrete time on this sample hold. And then that error here, difference between the real signal level to this discrete signal level, that's the quantization error, which is more or less, well, supposed to be less than half of the bit. All right, so before we start, real life signals, they are always analog, meaning continuous time, continuous value. Come on, oops. Then sampled signal, meaning discrete time, but still continuous value. And at the end, we have discrete time and quantized value. That's our digital signal. And that's the gap. Okay, so samples. Samples are characterized by the sampling rate. Actually, arbitrary time sampling is done only for, well, arbitrary purposes, like checking what is the temperature right now outside. You just, check it once in a while. But on the other hand, how that number came there, there are actually these small weather stations all around the world, huge amounts of them, and basically some server will get a value more or less once in 10 minutes or so. So it basically, it's sampled value. Without a constant fixed sampling rate, it's very hard to make any sort of filtering which makes sense. Yeah. Okay, so if you have a too long sampling interval, so too small sampling rate, you will get signal aliasing. Okay, blue line is a real one, but if you take samples only on those red lines here, you will get a aliased signal. Still looks like a sinusoid, but it's totally off. Totally off, but that's what it looks like. Alias. All right, yes, and digital signal is a quantized value, and they're actually just something to remember. Signal to quantization noise ratio is basically it's supposed to be better than your signal dynamic range. Then you are in a good shape with your sampling. Signal to quantization noise ratio. Okay, and that 1.761 comes from the fact that the quantization step size is the size of the least significant bit. Good. So, sampling again. Uh, Human ear actually detects roughly from 20 hertz to 20 kilohertz signals. To prevent aliasing, you need to have the sampling rate at least for 40 kilo samples per second, at least. So that's why actually we have this historic 44.1 kilohertz sampling rate on so-called CD quality audio. Still a kind of industry standard. And then the listening music, say any music, the normal sound pressure actually is quite high dynamic range. 20 dB is like a whisper, or dropping a pin to the floor when you are listening in 1 meter away. That's about 20 dB. You still can hear it, but of course everything else must be quite silent that you can recognize. Then 100 dB, okay, peaks can go up to that height, but 80 dB is already dBA, meaning the air pressure is the one. Above that one, the noise will start hurting your hearing. Okay, yeah, students, you still need to hear. Well, if you're getting the professor, maybe you don't have to. Haha. Okay, which means that we need at least 13 bits. At least 13 bits for CD quality audio. Okay, and that's why basically we have usually 16 bits A to D conversion for audio. More than that, actually, of course, bigger is better. So, okay, well, 24 bits, for example, or 32 bits. 32 bits audio means that, well, nobody will recognize the difference between that one and 24. 24 and 16 can be actually recognized if there's a huge variety of the audio levels. So in some classic music, maybe. But, this modern music, it sounds exactly the same. 16 bits is enough. All right, and that actually comes from the hearing, how human hearing actually works. Okay. Basic signals. Basic sampled signals. One of the basic signals, same as in analog world, there's a delta function. Dirac's delta, meaning that the amplitude goes to infinity at time 0. That's in analog world, but the energy is 1. Okay, that's the definition of a analog system. But the discrete Dirac's delta function basically is when you integrate, say, from -half to half, and so on. The Dirac's delta function, and basically you get 0 when the index n goes to 1. Value is 1 when the index is 0. Okay. Okay, let's go back to this one. So Dirac's delta function is more or less this analog version is kind of hard to use for any testing, but the impulse function, discrete Dirac's delta function, is the most important testing vector for discrete time systems, since you'll be measuring the impulse response. On analog systems, you are measuring the step response, because okay, on the function generator you can create a step quite well. It's this square wave. You just take long enough, then you can actually fit the edge and run it through the system, see what comes out. Okay, on digital world we have the Heaviside function, or well, step function. Heaviside function, meaning that, okay, it's just the sampled step function, unit step function. Not that often used on digital system testing, but used, yes, when you are measuring a analog system and sample it, sampled output. Testing an analog system with a digital oscilloscope or some other sampling system, you just put the right device under test here and run a square wave, and then have the digital sampling oscilloscope here, which basically has the sample and hold and the A to D conversion right there. Then you would get that something like that. It shows more like this, but anyways, in reality, it's a sample system. Good. How to get the delta function, the heaviside and heaviside to delta function? Quite easily, you can see if you take the delta function, take the heaviside function, and delay it by one time step. So fundamentally, your heaviside of n-1 would start here. If you subtract this from each other, you will get the delta function, which means that basically in here you will get the impulse response easily by taking that one and just filter it with the first order difference, meaning just the same stuff in here. Okay. The other way around this is not that practical anymore. Well, the heaviside is also the okay, I think there's an error here. K from 0 to infinity, delta n minus k, that would be the heaviside. And what this one actually says here, the last formula, it says that any arbitrary signal of x can be described as the as a sum of its parts, meaning any signal, for example, something like this. You can actually separate each of these points and do whatever you need to do for each of the point separately. It's superposition principle. Requires that the system is linear though, but anyways. All right, so let's see. So we had the impulse unit step, and then we have periodic signal. In analog domain, periodic signal is quite simple. You just find if there is a base period, and okay, it's easy to find, okay, those are the base period. Then you have the periodic signal, so it repeats itself. On sampled world, it's not that simple anymore. Analog signals, analog periodic signals are not periodicness on the sampled space at all. Only, say, arbitrarily made signals can be that way. So basically, this is the same, similar signal as earlier, but you can see that if you take a look at these red dots, here we have, it starts from 0. I cannot see the exactly the same spot at all here. So it does not repeat itself, at least not on this analog signal base period. Spectrum. Fourier series. Did you like the Fourier series in math class? Good. All right. So what does it actually say? Okay. If we know the base period, then we can basically make up the continuous space signal by weighted uh, sum of cosine and sine terms. So, okay, there is some meaning on it. What it actually gives you is a tool to analyze a system both in time space or frequency space. You just make the spectral components out of the signal. Oops. Okay, random. Random signal means that it has unpredictable value. Not deterministic like, sinusoids or, well, some other well-formed signals, but more like what nature does for you. Wind noise in microphone, that's, say, small-scale star turbulence makes the wind noise, and it's totally arbitrary. You cannot get rid of it 100%. You can reduce it by some filtering, but you cannot get rid of it totally. Shot noise in electronics. Okay, shot noise, remember that one? When you have current is actually carried by electrons. Okay, electrons or holes, but on the other hand, hole is still, it remains at the same place. You just have the electron which is jumping from one hole to another. And the higher you have the current, more you have the shot noise. Johnson noise, meaning that if you have a conductor or semiconductor, then this variance of the Johnson noise depends linearly from the temperature. Again, you cannot get rid of neither of those. If you don't have any current, then you don't have any signal. If you don't have any temperature, then, well, good luck. Okay, so there's only, you can actually, on this laboratory environment, you can go down to liquid nitrogen level practically. Going lower than that, let's see, was it liquid helium which goes lower than that? But still, it doesn't reduce the that Johnson noise more than, say, tens of percent. Okay, so with the Johnson noise, you just need to live with. You can do something usually for the impedance, but not always. For example, if you have a sensor, resistive sensor, then you cannot do anything about this one. It just have the noise what it has. Okay, so we have natural noise sources. And natural processes. You have two random processes actually, or models. Two random process models. One is Poisson distribution, meaning rolling the dice, or normal distribution. And then there's the number of okay. With big numbers, usually any random signal will go close to the so-called normal distribution. Okay, it's quite hard to say which distribution would have this, since they are in time space. But if we basically do some calculus and do the histograms, meaning the frequency of each value, Fosson has this kind of nice the skewed bell curve, only positive values, and then normal distribution has this nice Gaussian shape. The histogram. And well, this is never exactly Gaussian because of the noise. The random numbers appear randomly. So there's a variation on of the values right here. Good. Ooh. Correlation. Have you covered that one in mathematics or some other class? Correlation. Yeah, maybe. You don't remember much. It's usually it's full at the middle of some other course. Okay, correlation basically the cross correlation measures the similarity between real signals X and Y. Similarity. Okay, and basically what you do is you will have two signals X and Y and start shifting the other one with different time lag right here, and that would be a time lag of 3, 2, 1. No. Let's see. 3, 2, 1, 0, and minus the same thing. So basically, and on each of these, you will multiply the terms and then calculate the sum. And here, where you have everything is matching, you have high number on the each of these pins, and then when you calculate the sum, you get the highest peak. Very high correlation when you have the time lag 0. If I had the middle finger somewhere in here, then I would have the high correlation right here. Okay. Or missing a finger. Then you have about the same correlation on both of these places. But anyways, it's such a calculation of similarity. Nothing more. Autocorrelation. Autocorrelation measures the self-similarity. How similar a signal is to itself. Okay. This makes sense if you think of if you're trying to find repeating elements on long signal. For example, you have something like that. Ooh, that looks like EKG, right? You run the autocorrelation, you will actually then get a peak. Well, first peak would be at the beginning. The autocorrelation would have distinct peaks on a place which also tells the base period of the signal. Okay, so that would be the measurement of a path width, which also some sort of makes an average. Otherwise, you could actually take it a look from, just calculate that one from peak to peak. But how about if you have, say, the sensors are a little bit off, or there's some noise? Then you really need to autocorrelation to get rid of those noisy factors. All right. All right, and that's basically if you have the power of two elements on your system, then you basically can go and do the correlation on the frequency space, meaning the Fourier transformation. But okay, I think we will cover it later. Some examples of correlation where it's used. Acoustic radar. Short pulse from loudspeaker, and then basically microphone listens both the sending pulse and then the one comes back. All right, so loudspeaker, microphone. There is the reflecting object. So we have some of the signal coming back, meaning that it first gets the direct signal at time 0, maybe chirp like that one, and then the reflected signal somewhere here, which has the same signature. And again, autocorrelation would actually clean this one up, and you will get a big peak here, and then also a distinct peak at the time that it takes for this sound to go there and come back. That's the simple acoustic radar principle. Right. Convolution. Convolution is almost like correlation, but instead of, okay, this was the correlation. Instead of the doing, piece by piece, you will time reverse the other one, and then basically do the same thing as in correlation. Why? Basically, the linear filtering. Woo. Filtering is based on convolution. Spectrum space. Low pass filter in spectrum space. That's plus and this is minus. That's a cutoff frequency to cutoff frequency. So that's our low pass filter. So it passes all the signals between minus omega c to omega c. And think of multiplying a signal in frequency space, meaning that you have the spectrum of the signal somewhere, something like this, the complex spectrum. That's the x of omega. If you want to filter, low pass filter in spectrum space, you will just multiply this signal in spectrum space with the system frequency, the response, or well, practically the S, the S transform, Laplace transform. But anyways, then you get the output y of omega equals h of omega times x of omega. Okay, when you basically do the transformation to the time space, since the time signals, or only time space signals make sense for the human ear. Okay, you basically get the y of, let's make it t is the same as h of t convolution. Did I make it like that? No, I actually did convolution with x of t. So that's where we need the convolution. And that gives the reverse time operation on the second parameter here. Nothing fancy. It's just calculation. Okay. Signal to noise ratio. Yeah, it's defined. Yes, excellent. Spectrum analysis. Okay. So we did something on the spectrum space already. The power spectrum describes the distribution of signal power into frequency components, meaning that if you have any signal and you want to break it into spectral components, you just do the Fourier transformation and then some. Okay, nothing fancy about it. Oh, right, except in sampled signals, you will get so-called Gibbs effect. This is an actual sampled sinusoid spectrum. There's the exactly 50 Hertz right here. Then it also have these envelopes, which comes from the fact that our sampled signal was windowed. So it wasn't just the sinusoid, but it also had the rectangular window used to sample it. Mathematically, that's the only way you can actually produce a set of, okay, if we have a continuous time signal, and you want to take a certain sample, if you'll basically break just that part and analyze that one. And it's the same as multiplying the signal with square-shaped window or some other shaped window. But anyways, you will get that window actually causes these envelopes. Good. Then the spectrum analysis, more spectrum analysis. Spectrogram. Spectrogram is simply time series of spectra of subsample data, meaning spectrogram has shows how the frequency of the signal changes by time. It's kind of spectral signature of the signal. Wow. Good. That was the brief reminder of the theory part. That was a theory of practice. Okay. Lab. How about if we now have a short break, and you can during the break you can download the MATLAB to your computers. Okay, good. So we will continue at some point.